Welcome to the screencast on infinite series. Yes, I did say infinite. Up until now, we have been finding what are called partial sums. In other words, this notation of S13 meant add up the first 13 numbers. And even things that where I asked you to get the sum like 33 plus 35 plus ... 39. Even things like that where I didn't use the S notation, the 39 implies some ending point. So we've been adding up a finite or countable amount of numbers. So now we're going to transition into what's called infinite series. And you'll see that in some cases you can actually find the sum even if the series goes on and on forever. Let's take a look at some and think about whether we could get an infinite series. If I had something like this, 2 plus 4 plus 6 plus 8 plus ... Do you think it would be possible to get a sum overall of all of the numbers? Think about it for a second. I think these numbers are just going to get bigger and bigger without bound, and that no matter how many I add up, there's always another number which is even bigger that I'll have to throw into the sum. That I'd never end, and this number would continue to grow. This sum that I would get would continue to grow on and on. Notice this is an arithmetic. It's your simple add a certain amount every time. And basically, no infinite sum is possible. So there will be certain problems that you'll encounter that we won't be able to do, and you'll be done the problem as soon as you've told me that it can't be done and why. And the answer for why we'll discuss in a little more detail afterwards, but for now, it's just because it's arithmetic. You might say, well, what about the arithmetics where the numbers are going down? So for instance, 20 plus 15 plus 10, ... Well, here, it may seem like the numbers are getting smaller, but eventually they're going to go into the negatives. And there'll always be another negative number to add in. So picture that counting by fives downward, that, I'm at negative 200, then negative 205, and this continues on to negative a billion, negative 1,000,000,005, and it just continues on without bound. There's no way to get a sum of all these numbers overall, so this one is also not possible. By not possible, again, I mean not possible to get an infinite sum. Certainly we've been getting partial sums of these. Now let's look at a simple version of a geometric. If I have something like 2 plus 12 plus 72 plus 432 plus ... This one is geometric because I'm multiplying by 6 every time. So it's not arithmetic like the last two. So maybe this one can be done. But as you can probably see, these numbers are getting bigger and bigger. And if we were trying to add them all up infinitely, well, the numbers would just grow without any boundary. And the number that represents the sum is just going to get bigger and bigger too, forever. So we'll never be able to get a sum of all numbers because it just keeps on growing. So in this case, with our geometric, if it keeps on growing, it can't be done. So no infinite sum is possible. So, you just saw me use a word growing. Possible. The word growing, actually there's a word for that. And the word for that is diverging. So this is a series, but it is diverging, meaning it's getting larger and larger without bound. And therefore no infinite sum is possible. So now we're going to transition to the one case where maybe we could get an infinite sum. Before I delve into this, I'm going to draw an aerial picture for you. Let's assume that this is a wall, and this is me standing a certain distance away from the wall. Let's say I'm standing 20 feet from the wall. So let's say I decide I'm going to walk half the distance to the wall each time. So the first time I walk, I move to here, and I've traveled 10 feet. I'm going to just keep a little record of how far I've traveled so far. And then I travel halfway to the wall again. Well, there's 10 feet left, so to go halfway would be to go 5. So now my sum looks like this. I've traveled a total of 15 feet, right? And then I travel half the distance again. So I go from here to here, and that's going to be a 2.5, 2.5. And now I'm going to travel half of what remains again, and that's going to be, I already had the red marker, I'm going to travel half of 2.5, which is 1.25. So first of all, let's take a look at this series and notice that it is geometric. My R value is 1/2. That's what's causing the numbers to go down in size. Does it make sense to you that if I walk from here to the wall, the most I'm going to travel is 20 feet. I'll run into the wall. My destination is the wall. So I know my sum can't exceed 20. This is an example of a geometric series that is actually not getting larger in size, but the actual terms within it are shrinking. The word for this getting smaller or shrinking is it's converging on 0. Meaning that the sizes of the terms themselves are heading towards 0. The more and more times I multiply by 1/2, the smaller the numbers become. Basically, this is the one kind of series that we'll be able to get an infinite sum with. A geometric series where the numbers are shrinking in size. The reason they're shrinking in size is because R is 1/2, which is a number smaller than 1. Whenever you multiply by numbers smaller than 1, the resulting number is always smaller than what you started with. So this is the one case where we have a geometric series that is converging to 0. The size of the terms are shrinking down towards 0. And this is the one case where an infinite sum is possible. So now let's take a look at how you would actually calculate that sum. You're going to love the formula. It's really small. It looks like this. The sum equals the first term divided by 1 minus R. That's the entire formula. Notice with this formula that it's just an S right here. There's no N. Remember, it's not a partial sum. It's not a sum out to the 18th term or something like that. So there's no N value here saying only add the numbers that are to this particular term. So this S without that little n means the total sum. The sum of all terms, infinitely. This t sub 1 is the same t sub 1 you're used to seeing. It's just the first term. And that r value is the same thing again. It's the ratio that we're multiplying by every time. It's that fractional amount that's smaller than 1 that we're multiplying by repeatedly that's causing the terms to get smaller. This formula in blue should look an awful lot like the formula we've been using for a geometric series before. This earlier formula that we had, notice this right here, if we were to cross it out, would make the formula look just like this. So essentially, the blue formula is just this formula with this crossed out. The n goes away because we're no longer adding just out to a particular location. We're adding all of the numbers. So this blue formula is the one we're going to be using, and I'm going to show you how to use it to get the sum of the numbers that we started on the previous slide when I was walking towards the wall. Remember, I started 20 feet away, so my first distance traveled was 10 because I was walking halfway to the wall. Now I'm 10 feet away and I walk halfway again. So now I've walked 5 feet. Now I go halfway again. That was the 2.5. And then half of that distance that remained was 1.25. And this would continue forever and ever with the 1/2 being the r value. So r is 1/2. To use this formula, we have s is equal to the first term divided by 1 minus 1/2. And you can do this certainly on your calculator. If you were doing it by hand, you'd go 10 divided by, and 1 minus 1/2 also is 1/2. And then we don't leave fractions in the denominator. We end up saying 10 times the reciprocal of the two. So notice it comes out to be 20, which by coincidence was that distance that I started away from the wall to begin with. And we knew that we couldn't walk to the wall and walk more than 20 feet. That made sense to us. So there, we've just done our first infinite sum. As a recap, basically understand that no infinite sum is possible when you have any arithmetic, whether it's counting up or counting down. So no infinite sum is possible if it's arithmetic or if it's geometric and growing. And by growing, I mean the sizes of the terms. Okay. And an infinite sum can be found using this formula right here whenever the series is geometric and the term sizes are getting smaller, or we say converging on 0. We're going to now have a few problems for you to do for homework, and that'll be all you have to do for this weekend.